we will learn how to fit an impedance spectra using the XSIM Studio ECS software. The impedance has been measured between 1 MHz to 0.1 mHz frequency with an amplitude signal of 10 mV. So here we have an impedance spectra of a 3-electrode electrochemical cell. To do the impedance fitting, we will first visualize the impedance results and get them into either the Bode plot or the Nyquist complex curve. For some researchers or electrochemists, one of these plots might be more familiar. This is the complex curve visualization of the impedance results. To begin with its fitting, we will first magnify its higher frequency part. Now we go to the Fitting tab and choose the equivalent circuit as the fitting method. To begin with equivalent circuit fitting, we will design the circuit. Here, we take 2 resistors and a constant phase element to begin the fitting. R1 corresponds to the ohmic drop, R2 corresponds to the charge transfer resistance, and the constant phase element provides the non-ideal capacitive behavior of the double layer in the electrochemical cell. We must draw the lines to complete the circuit. Click the Adjust button to adjust the circuit. Now we will feed in the initial values for these parameters with which we can begin the fitting. Here we see that the high-frequency impedance spectra, for example, for 1 MHz frequency point, is approaching to the origin, therefore, R1 could be a very small value. R2 is nearly approaching a 3000 ohm on the real axis and, therefore, we can put this as an initial value. For CPE1, first, we must allow it to be modified to free or positive. And when we double-click on 3 dots, we can also modify other parameters. With this, we will define initially 2 data points between which we are trying this equivalent circuit, which is designated as A and B. And now we click Run. We see that this part of the overall impedance spectra can be fitted well with the equivalent circuit. Now we will extend this point B by deleting at older location and taking it somewhere further on the spectrum. We also need to modify the equivalent circuit to fit the additional part. To do this, here we would utilize another resistor and, in parallel of it, a constant phase element. Connect the line to complete the circuit, click Adjust, and provide initial values to the newly added elements. With this, and with new data points selected, we will click Run, and we can see that the impedance spectra can be fitted for the points we have selected. Now we will reposition the point B on impedance spectra and keep fitting the curve. Keep repeating this process until we get considerable deviation between the fitted and measured impedance. As the impedance fitting is now deviating from the original impedance results, we would have to modify our equivalent circuit so that we can fit the results properly. The selected point B is near to 0.5 Hz frequency and in such a low frequency regime, the diffusional polarization of the electrochemical system might dominate the impedance results. The diffusional impedance or polarization is usually represented by the Warburg open or Warburg short element. This is depending upon the type of diffusion, which could be finite, semi-infinite, or infinite type of diffusion. So, here we add a Warburg short element to the existing circuit. Allow the Warburg element to modify itself freely or positively. We would now try to fit the results where we are exactly at this point and systematically increase the low frequency point to fit more and more of the spectrum with the equivalent circuit which we have produced. So, here we have successfully fitted whole of the impedance spectra using the equivalent circuit we have designed. We may also get out these equivalent fitting parameters out and correlate them for their physical significance related to the electrochemistry of our cell. We may also want to find out if the equivalent circuit or if the fitting has a certain error. What we see here is R1 and R2, which are the resistors related to ohmic and charge transfer polarization, do not have significant errors. However, R3 does show us a high amount of error. This is because R3 is being associated with the diffusional polarization, which we have fitted with the R3, CPE2, and the Warburg short element 1. When we want to fit the overall impedance results from really high frequency point to a really low frequency point, there could be one or more elements with really huge errors, but we would have to neglect it. With impedance spectroscopy, it would be really important to know which frequency range is most important for our studies. Measuring or fitting a part of impedance spectrum can help us avoid such fitting errors. With this fitted result, we can save the equivalent circuit, which we have used for this fitting for future usage. Also, we can go to Graph Setup and click Save so that we can create a graph which does have the equivalent circuit with its correct values, and the impedance spectra is fitted. This all can also be saved as a project. We hope this video helps you with fitting your impedance results. Thank you for watching.